Hi everybody, welcome to another video in Math 1324 section 3.4 present values of an annuity amortization. Right, so we have this just straight with the formula. We said the present values is given by this formula because payment we know how to calculate I from the previous section and N from the previous section. Right, let's just talk about that again. So payment, periodic payment is PMT. I is the rate per period. I equal R over M and N equal M over T, where N is the number of payments or the number of periods. Because M is the number of period a year. Number of payments or periods per year. And payments are made at the end of each period. So of course that's formula, but what it actually calculate. So now think about this. This is in reverse. So let's say this is the second part of the retirement. So let's say you reach the retirement age and they give you $1 million, and that to be of course that you save for the whole life. And then with that $1 million you want to spend in, let's say, 20 years or 10 years, and you want to get payment every month. So in that case, how much would we get? So the present values is what we have now, and then they just give you back from that big lump sum of money, and that over the time I will give you back some amount of money. So like if you win a lottery and you put all the money into the bank and you said, oh, I'm going to withdraw that over the next 30 years, how much we get each year, for example, something like that. That amount that you win or to put in the bank, that is the present values of an annuity. So here's how much money must be deposited now. So the question usually clear enough. We said how much, so that amount must be deposited now, so you know that have to be the present values. 6% interest compounded, so in that case we ask for the present values. And it is interest rate 6%, 0.06 quarterly, so 6% quarterly. In order to withdraw, so this is the payment that we'll have for 2 years. Right. So first we calculate I and N. I is the rate per each payment, the interest rate for each payment, divided by M. So you have 0.06 divided by 4, so that gives us 0.015. And then N is the number of payments, MT. M 4 times a year for 2 years, so it's 8. Now we have that. Now the present values will be equal to the payment times 1 minus 1 plus I to the negative N over I. So we have 3,000 1 minus 1 plus the interest rate per period to the negative N, negative 8 over I. So 3,000 times a fraction of 1 minus 1 plus 0.015 to the negative 8 divided by 0.015, and we have that. So that's $22,457.78. Right. So if we have that amount put in the bank, we would be able to withdraw $3,000 every quarters for the next 2 years, given that 6% interest rate. Right. Now, of course, we talked about the calculator last section already, so we'll briefly go through this again. So hit apps and then enter twice. N is the number of payments 4 times a year for 2 years. Interest rate 6. Present values, we don't know, so leave that blank. Payment, we received 3,000, so that is a plus positive 3,000. Future values, we will not have anything. Compounded 4 times a year. Now we solve for alpha and solve for that, and this is negative, so that means we have to deposit that out of our pocket, so that's why this is negative. Positive 3,000, meaning that we receive the payments. Right. Now suppose the core settlement result in that much award. It is invested at 9% compounded semi-annually. How will it provide at the end of each half year for 7 years? So in this case, we have right now is that, and we put in the bank, but still out of our pocket into the bank. So the present balance is if it is invested 9%, so all of that we put in the bank, and it is invested 9% semi-annually 2 times a year. How much will it provide at the end of each half year? So in that case, this problem asks for the payments. Right. So what do we do? Now we have present values from the previous page topic, which is that payment equal to 1 minus 1 plus I to the negative n times I. Now, if we want to solve for payment, all we need to do is just flip that, multiply the reciprocal on both sides, so the payment will be equal to the present values times. Now we just multiply that, flip on both sides. So now we have fit that amount. The I, we need to calculate the I and the N. I is equal to R over M, 9%, 2 times a year. N is equal to MT, 2 times a year for 7 years. So So we have 0.045 1 minus 1 plus 0.045 to the negative 14, right? We do this by hand using the calculator first. So we have that much. Sorry, 73,265 and 24 cents. Right, now if we use that F, payment number payment 2 times a year for 7 years, interest rate 9%, present values we give to the bank, and payment we don't know, just leave it blank, and compound it 2 times a year. Right, and now we solve for the payment alpha and of course that's what we have. So just one formula. If we want the present value, we use that. If we want the payment, we just flip it to the other side, and that's what we have. Of course we can use the calculator as well. Next, lottery prize worth of that much is awarded in payments of end payments of $10,000 at the end of each month for 10 years. Suppose money is worth 7.8 compounded monthly. What is the actual values of the prize? Right. So here's the thing. Whenever the big amount of that we say you win some money, like big lotteries, in the millions and maybe billions, they're not going to give you all of that at the same time. What they actually give you is just, by the way, I forgot to mention, if you want to quick hit second mode to quick get back to home screen. Right, now back to the story of lottery. If you win a very big amount, they're not going to give you all at once. They're going to give you in payments, usually in years, and sometimes 30 years. So in that case, whatever they say it is, let's say $1 billion, you're not going to get the actual $1 billion. You get $1 billion in 30 years, but in terms of the money now, it's not going to be $1 billion, because whatever the money now is worth more than whatever $1 now is more values in the future. So in that case, they just give you that over the period of time, so it's actually less than the advertised amount. So here we have $10,000 at the end of each month for 10 years. So 10 years each month, so M is 10 for monthly, 12 for monthly, T is 10 for 10 years, and then the rate, this is 7.8%. And what is the actual values? So the actual values that you win now is to be determined. You'll find out that's going to be a lot less than $1.2 million here. Alright, so we have this. So first we calculate R, I, the interest for each period, 0.078 divided by 12. 0.065, and then M, the number of payments, 10 years, 12 times a year, so that's 120. I should write N equal to M times T and 12 times 10, but regardless, that's 120 payments. And because if you take 120, you multiply by 10,000, that gives us the $1.2 million as advertised. But we're actually not getting that much if we want all of the money now. I want to write the formula first, right? So payments, $10,000. One plus the interest rate per period, and is negative 120 over I. So as you see, we actually only get this much using today's money. Right. Actually, I should switch to the old calculator and see how that feels. Right now, this is a typical calculator, scientific calculator. You enter like this: 10,000. Multiply the top. You need one parentheses for the top. And then that raised to the power of the negative. You use this negative sign and not subtract. And then you close it. So that is for the top. And now we divide by the bottom, only one term, we don't need the parentheses. But you have the same thing. Let's see what the calculator get. Alright, 12 times a year. 12 times a year for 10 years. The interest rate 7.8. Present values we don't know, just give it 0. And payment we get 10,000. Future value is none. Remember, I did mention on the previous section these three things: one positive, one negative, and one zero. The middle three. 12 times a year. Right. Now we solve for the present values. As you see, one negative, one positive, one zero, as always. So that's negative. So that means we have to put in the bank or whatever it is. Give that to the bank. So the bank will give us the money at 10,000 each month for the next 10 years. An inheritance of that much is invested 9% compounded monthly. If it is withdraw 2,500 at the end of each month, how long will it be until the account balance is 0? So in that case, the question asks for how long. So in this case, the formula here will not work to solve for time. So won't be able to solve for n here. Of course we can, but that's complicated. So I recommend, if the question asking for the rate, if the question asks for the time, just go ahead and use the calculator. So let's summarize. So this is invested, so that's the present values. We have that at the moment. 9% compounded monthly. Monthly. And if the amount is withdrawn at the end of each month, how long we would take? So let's say how many years. Right, so write what the calculator usually have. And interest rate, present values, payments, future values. We know future values will be 0. The last two usually the same. The last two are the same, so we just have that together. Right, and with question mark, we don't know. So at the moment, just put 0 there for a moment. Interest rate 9. Present values. This is invested, so out of our pocket. We're going to get back our pocket, so that's negative. We're going to get back 2,500 each month. This is monthly, so it will be 12. Of course, this we're going to solve for n. So that's for alpha and enter. Right, so we don't know what n is. We know the rate is 9%. Present values, we invest $250,000 and we get back 2,500. Future value 0. Payment per year, so we have 12. This monthly. All right. So in that case, so we have that much. So n, the I is 9, and so pretty much that. So alpha and so we have 185. So n is equal to 185. But we have to take this and divide by 12 because there are 12 times a year. So we get that in about 15.46 years. Right, now, of course, if you have that amount with no interest, 250,000 divided by 2,500 is 100. So if with no interest, you can only get in 100 payments. So that's about 8 or 9 years. 8 or 9 years. But with the interest, you can actually stretch that to about 15 and a half years. So that is the present values of the annuity. Next, amortization. Well, exactly what I like, what we have. So the formula where n payment amounts needed to amortize present values if the interest is for each period is I. So amortize meaning to kill something off. For example, if we buy a house, how much do we need to make each month for the next 30 years to pay off that house? So that is the type of the problem that we're dealing with. So let's say a bank loans 50,000 at 4.5% interest per year to purchase a house. The customer agreed to make monthly payment for the next 15 years. How much should the amount monthly payment be? So again, if we ask for the middle three, present values, payment, or future values, there's formula for it. Unless we ask for time and we ask for rate, then we rely on the app. Alright, so in this case, let's write down everything we have. The bank loan, this, so that will be the present values. At the moment we have that much. and a 4.5 interest rate. The customer agreed to make monthly payment for the next 15 years. So M is monthly payments, 12 times a year, and next 15 years. How much the payment will be? Pretty much straightforward. So this payment will be made in the next 15 years. We pay off that amount. Right, so we'll calculate I, the interest rate per period, R over M, R over M. N is equal to MT, 12 times a year for 15 years. So payment, present values, I over 1 minus 1 plus I to the negative N. Present values, 50,000. Interest per period, that much. Right. So 500,000 times. The top only have one number, so we don't need the parentheses for that. The bottom is more than one term, so we need the parentheses. 1 minus another parentheses. 1 plus 0.00375 to the power of. We really don't need parentheses here, but to be safe, I'm just going to use that. Close. So the payment of 382.50 cents. We round to the 2 decimal places. Right, now let's use the app. Alright, so we will make 12 payments per year for the next 15 years. The interest rate is 4.5. Present values, the bank give us 50,000, so that's going to be positive. Payment, don't know, but we will determine that later. Future values is none. And now we have 12 times a year. So we will solve for the payment alpha and of course that is negative. Right. Next, construct the amortization schedule for 10,000 with interest 10% to be repaid in 5 equal annual payments. Right. We will not do that for a lot, but right. So this is what we do. Like we will not complete the problem, but we get the idea. We do a few steps and then you get the idea of the problem. So do we pay off that? So that is the present values. So we have present value. Let's just write out what we have. The interest rate 10% and 5 equal payments. So interest rate, annual payments, so once a year. 5 years. First, let's calculate the payment amount, and then we go from there. I'm just going to use a calculator here so that we're quicker, because the idea is it's not to find the payment. The idea is how to construct a statement, if you will. Right. Number of payments, 1 times a year for 5 years. That's 5. Interest rate 10. A loan, so they give us the money of $10,000. Payment we don't know. Just keep 0 for a moment. Future value is 0. 1 payment a year. Right. Now we calculate that. So after we use the formula, the payment is $2,637.97. Right. Now to construct the amortization schedule for 5 months, that would be a lot. So there would be enough space here. So just do for the first years. So after the first year, of course, come up. I'll show the first years. So this is the end of year 1. Now we're going to make the payment that for the first year for sure. But what is the interest? The interest is going to be $10,000. The interest for 1 period. So that gives us the interest of $1,000. So the interest for the first year is that much. Now, but we make that payment. So this payment have to subtract 10,000 toward the interest, right? So the payments. So the bill you said, how you see is that is $2,637.97. That's the payment, and this amount toward interest is 1,000, and then 2 for principal. Of course, you make that payment, subtract 1,000, you have $1,637.97. So that much will go toward the principal. So that is after year 1. That's how it works. Now for year 2. First, we no longer have $10,000 as a present value because we pay off a little bit of the 10,000. So the amounts now, let's say the present value at that time of the 2 years is going to be 10,000 minus this. And so the amount now, before we make any payments, is 10,000 minus 1,637.97. So we have 8,362.03. Now we still make the same payment. But the toward interest, we haven't calculated interest, haven't we? Sorry. The interest is going to be this amount times the interest rate of 10%. So that gives us 86.20. So the interest now is only this much. So we still make that amount, that payment, but now toward interest it's going to be 836.20, and then the toward principal So we make this much money. I mean, we make this much payment. And but only 836.2. So that gives us 1801.77. So we that much will go toward the principal. As you see, over the time, the present the amount will reduce, and so the interest will reduce, and the same amount that we make less and less to our interest and more to the principal. Let's do that for one more time for year 3, and after year 5 it will be the amount will go to 0. So the amount now is going to be that's previous balance, subtract from the previous the amount that go to the principal on the previous amount, previous payment. So we have that. So we have 8362 minus, we can still do that. If not, then you just have to enter the number again. So you have 6,560.23. Next, calculate interest for that. It's going to be 10% of that. Now the payment that we make on that month, of course, still the same amount, but toward interest. Is that much. And then toward the principal. The last payment, let's do this first. So we get 2,637.97, subtract 656.02, so 1,981.95, and we just keep doing that. Oh, sorry, this is year 3. At year 5, when we make the payment, all of that will go to the principal, and that will reduce the balance to 0. Right. So like I said, just do a few steps, and then so you get the idea of how to structure or schedule of the amortization. Right. Next, we just have this, which is the unpaid balance. For a lot of end payments, payment, an unpaid balance, or the pay up amount after K payment have been made. So let's say we buy a house, and this to be paid off for 30 years. But we decide that we win the lottery when you after 10 years. So of course you want to pay off that. So in that case, that will be the unpaid balance that you need to be paid. So the formula for the unpaid balance after, so originally you need to pay off in end payments. So after K payment, the present values, the unpaid balance is equal to the present values of an annuity with N minus K payments, i.e. the unpaid balance is equal to this. And look at an example. Suppose a loan has an interest rate of that, compound monthly for 20 months. Given the monthly payment is that, calculate the unpaid balance after 12 months. So this is to be paid off in 20 months. But we decide after 12 months, after 12 payment, we want to pay off that. So what would be the unpaid balance? Right, so we have here the rate compounded monthly, so R 2.4% monthly for 20, so N is equal to 20 months, 20 payments. Now we decide that unpaid balance after 12 months. So after 12 months, K will be 12. What will be the unpaid balance? Given that the payment, the payment is equal to, PMT 220. So unpaid balance payment 1 minus 1 plus I to the negative N minus K over I. So in particular, we have unpaid balance, the payments of 220, 1 minus 1 plus the I. We haven't calculated that yet. So 0.024 divided by 12. You have 0.002. To the negative N of 20 minus 12 over I. Right, 220 payments times I is 0.002. Big parentheses 1 minus 1 plus 0.002 to the power of negative 20 minus 12, that's 8. Just put 8. So that the whole on the top divided by 0.002. So that's what we have. So the unpaid balance or the payoff amount is this much. So 8 more payments make, so that is the payoff amount. Right, and with that, we finish section 3.4. As always, thank you for watching and see you in another video in Math 1324.